Welcome everybody to the last lecture of this year series. Today I am connecting from the Scuola Superiore Sant'Anna in Pontedera, Pisa. And needless to say, we have a very cool and interesting list of lectures today. The first one will be background lecture by Rolf on what we may expect from the next generation of robots and in general intelligent machines. Then at 9:55, after the coffee break, we will have Barbara Mazzolai, which will actually give a talk for which I tried to create some expectation in the past lectures, because she will talk about plant robots. And you know that there is a very much quoted saying concept by David Wolpert about why do animals have brains? Because they need to move. So it will be interesting to see that also plants have some kind of intelligence, and might be a nice topic for discussion to see what we really mean, no? With these intelligent plants. No? So, you know, she loves a lot plants, and she wants to say that they are intelligent. I don't know why. And then we will have another presentation by Professor Nefti Mezziani from Salford about how robotics could help sustainable manufacturing. Also, Barbara is a professor, just to. And then we will have a student presentation by Jarek Sporitzik. At any time, this is now for next year, if you want to plan a student presentation, short student presentation on some topic, please just contact us. And then we will have a very short round table with all of us about what we can expect from the future of robotics and intelligent systems. And then we will have to say goodbye. And so the next speaker will be a student, Jarek Sporitz from Poland. Are you ready?
Okay, so I'll try to get quick with that. So hello, and it's a pleasure to have this talk. My name is Jarek Sporitz. I'm a student of physics in Krakow University of Technology, and I wanted to say 2 words, maybe even it will be three words about my ongoing research in my master's degree, master's thesis. So yeah, let's start with this. Basically, what I wanted to do was developing of environment in which you would be able to build brick by brick from Lego-like rigid bodies and joints and motors, creature, a machine, then to program it, parameterize it, and to run some kind of evolution on it. I mean, some genetic algorithm-driven evolution to see how could it perform some tasks. So yeah, obviously one of the primary inspirations for this work was Carl Sims' work. He's evolved virtual creatures. Yeah, it's pretty cool. It is creatures that they evolved to do different kind of tasks: jumping, flying, swimming. And the second one was, yeah, it stunned me. I mean, the Breitenberg vehicles, the way they learn with a sensory motor action, the way they learn how to be, they learn how sense test environment, how to love things, how to hate things, how to be curious. So yeah, step by step, how did I approach the problem? So I created a very simple two-dimensional physics simulation engine. Pretty much something you see in every today game in mobile phones and stuff. So it pretty much resembles engines like Box 2D and Chipmunk, which was the primary source for the numerical engine. And yeah, I built it from scratch, so I know basically what's going on inside, to be able to, when time comes, to put into some more advanced motor propulsion, so like different kind of torque propulsion. Yeah, so with that I can build agents, kind of mobile units, and you can do that with any type of construction element, rigid bodies, joints, motors, actuators, sensors, of course, and kind of virtual CPU internal language that you could program the machine and actually program it in a way that you do with real devices, so microcontrollers. So yeah, that's a small sample of the developed language. So it pretty much resembles the assembler language, which has its own, mnemonics, device control codes like sensor get position, sensor get velocity, etc., etc. So yeah, it was also important to have this language to be able to measure the way of computational power given to a machine, to a particular agent. So we'll be able to actually be equal in computations he does with other agents. So yeah, we got the machine, his program, we can parameterize it. After parameterizing, and it's pretty much anything you can think of, from size of construction elements to propulsion, work parameters, torque of an engine, or parameters of sensors, and internal virtual code that you supply for the machine, so you can actually parameterize the code. With that, you can create a genome for the machine. So you can actually choose which of the parameters will become genes for the forthgoing genetic algorithms computation. Yeah, so we land on the genetic algorithm model, and here we got pretty much the same that we should expect from a genetic algorithm, simple model. So we got crossover mutation, and I added something called strains, which is basically a different kind of island through the chain of generation with a separation from other chain generation, but they still run parallel, and you can kind of measure the way that some strain learns more than the other. I mean, it was more efficient than the other. It had a better fitness. So yeah, and a particular simulation cell, which is specific generation and strain, can have similar simulation work. So every simulation work can have a different number of agents, or it can have just one agent. With that, we built an evolution server. So this is an actual server that you can connect via TCP IP, and you can view what's going on inside, select an evolution node, which is a specific simulation species node, and you can connect with it with a Python connector. You can create scheme, a parametric machine, select a genotype for it, select already created type, already created machine, and run an evolution test. You can also, there's a wrapper, right, wrong, kind of connector. So yeah, could you, Nathan, please play the first movie? Yeah, so that pretty much is what the first species called Walker is. It looks like a computer game, but it actually is 4 rigid bodies connected with one spring in the middle and 2 motors. The motors are connected to the dorsal-like thing that is in the middle, and it basically rotates. And at the end of the kind of legs object, you can see or you cannot the orange things that are sensors, contact sensors, that when triggered will switch the polarization of motors. Basically, the motors will rotate in different directions. And it just moves from wall to wall. So there's the simple first test machine. And so then we selected the genotype. We parameterized the torso size mount point, which you level the torso to legs and the size of the legs. We ran it through genetic algorithms, and we got this learning curve. So it pretty much landed the same fitness, 3 strains, but with small differences in shape. So Nathan, if you could play the second movie. Yeah, so that's the lowest fitness, but the best in the second strain machine, and it's got enormously long torso, and still it slips a little bit. This is the better one. It's got definitely shorter torso, and thus it moves faster. And the third one, the best one, was it was strain 3. So it's got really short torso, and its torque, it enables it to do this stand-up pose, and higher, to lift the whole body upper, and it eventually is the fastest of the species. Okay. So another test was Walker with obstacles. So I just added the obstacles, and that was it. So could you play not on the third movie? Yeah. So this is it. This is even more enormously long species. It slows down by its torso being stopped with friction on this obstacle, but still it's from the longest beings, it's the fastest. This little fella is better. You see, it has a higher level torso, avoids contact with an obstacle. And the third one, the best one, is actually quite interesting one. Okay, yeah. So here you see this slipping motion over the obstacle. So it actually uses this obstacle to move faster. What's interesting is this creature, when it is put into the environment without the obstacle, it will move slower. So it will come shorter distance in a constant 60-second time. So it actually uses the obstacles to move, to beat the fitness. And yeah, the last test was a drone kind of species. So it was parameterized box that used the impulse engine propulsion. And the impulse engines basically generate the applied torque to a specific point with a specific frequency. So it generates short time impulses. And we parameterize few environment things like where should end the limit of flying for this creature, and where, of course, what should be the size of the body, and the impulse magnitude. So yeah, we could see what came from this simulation. Nathan, could you play the horse movie? Yeah, so that's it actually kind of flies, yes. So the fitness is measured by the number of contacts with walls, and it's also prioritized. So the left and right walls are less cost. They cost for collision is lesser than the upper and bottom floor and bottom. Yes, and so this is the best one. It actually performs better than my own parameterized kind of long box. It performs worse. So yeah, this is just to prove that the genetic algorithm works and invented something that was the most effective. And yeah, two funny things, and I'll be finishing. Yeah, actually, the machines started to act weird at some point, and at first I was honestly thinking they're cheating, but it came that they didn't. So they actually used the internal.
Excuse me for interrupting you. You have no more than 2 minutes from now on, because you already have exhausted your timing.
Right. Okay, so I'll be finishing right now. So you could probably just play the final movie, Nathan, the fifth movie. So this is weird kind of working thing, and it actually uses the flaw in the physics simulation engine to perform better. So it beats every walker in there twice as good. So its fitness is twice bigger because it actually decided to use this internal flaw in the simulation engine to compete the others. And it actually used the gene pool to promote it further. So the species, I needed to re-implement the physics engine to actually fix the bug to make it work again. So yeah, this is and I just want to say that end line of this research of actually evolving more creatures, more ways to walk, to swim, to jump, and of course having fun. So that's it. Thank you.
Thank you. Maybe we may get one question, because we are dramatically late.
Okay. So sorry again.
No, I say that if there is a question, otherwise I think you will be happy to answer questions from
Absolutely, yes.
Yeah. Okay. Thank you again.
Thanks.
Okay, we are almost done with this series of lectures, but actually you know that the lectures are ending today, but in particular the students who are involved know that we still have some activity which will last in January, which are the koans, the challenging project that many of you have dared to take. And now Martin will give a very short overview about the situation on the koans. So listen if you are working on a koan. Martin?
Okay, thank you, Fabio. Can you see my slides okay?
Yes.
Okay, yeah, all right, cool. All right, so I will just go over briefly where we are right now with the koans. As you know, we're today at the last lecture. The groups for the 2014 looks a bit like this. We have 12 groups of 4 to 5 students. So it's quite a nice collection of students that have volunteered. Thank you very much for volunteering and for joining this experiment. We have 8 international teaching assistants. Also, thank you very much for joining us and for helping out. It's exciting to be able to work with you, and we hope to get some good projects. We already see some really cool ideas coming out of these group projects, passive compliance, evolution of body and brain, symbol grounding. So there's a lot of interesting things the students are working on. The timeline looks like this. As we know, today is the deadline for the preliminary design report, and then you have the group presentations in the end of January. For the grading, we know that the preliminary design report is a small part, but the idea is that today you should share with your teaching assistant and document, a concise document, something like 4 pages, where you talk about ideas you've had, what you've talked about in the group, basically. It could be kind of a bit of a documentation of the design process, what plans you have for the work you will do in the next month, and more or less where you are right now. Again, feel free to be creative. And then the final group presentations will be basically via Google Hangouts or something similar, and will be evaluated by a presentation panel. If you need inspiration, I would suggest that you go to our Google Plus page for the koans, where you will see examples of the projects from last year. We had some great examples last year of people doing very interesting stuff. So I suggest you do that to get an idea of what people have done in the past, maybe build on other people's work. And keep checking the website, keep responding to your group members on the website, especially the koans page is important. If you still haven't heard from some of your members in your group, or if you haven't gotten started yet, please contact us today so we can help you get started. We can talk about an extension for this first deadline if need be, but please get in touch, okay? And that's it for me. If anyone has any questions, feel free, or I guess we're almost out of time. Are you? That's it from me, basically.
Okay, thank you, Martin. So these koans are actually an important part of these lectures because it's where you put at work the ideas that you should have grasped, and if you didn't grasp them, trying to cope with the challenges, you should be led to grasp them. So now we are really almost to the end of the lecture, not I would say of the whole process. And we have scheduled, actually we are dramatically late, so we may dedicate 10 to 20 minutes if you want to go a bit after the scheduled ending. About the future trends, I mean, it has to be a very short discussion, but maybe it's good in particular for people in Japan or China. So I think we may try to give an answer to 2 big questions. One is where you see and this is open to everybody. I will start with the 2 guest lectures if at least one is still here because it's close to me. So 2 things. Where you see the biggest roadblock, so things that we don't know that we should know, or things that we don't do but we should do to achieve the full potential of embodied AI, so the concept that we are selling here. And where you see the already existing opportunities, so the low-hanging fruits, as they say. So what we could easily do if we just put easily, what we can do without any new scientific insight we could already do today. So we can do 2 rounds. The first round is where you see a bigger roadblock, and I think we may start from the first guest lecturer.
Because I'm here.
Because I see.
Yeah.
Because, okay.
But of course, this is just a personal
of course,
vision of the problem. From my point of view, the most not critical, but probably we have to work more on the interaction among disciplines in order, if we want to talk about embodied intelligence and something that is more close to living systems, and they are more soft, are more intelligent, and more active in interacting with the environment, with other living systems. We need to really have a group that talk each other, but come from biology, come from materials, come from engineering, of course. So we really need to increase the basic knowledge in this field. So it's not. Of course, we need to see in front of us the applications, and probably this is really clear, and so in order to reply also to the other aspects. So from my point of view, what is clear is the future application, this kind of robot. So we have in mind many different fields of these soft, more embodied intelligent robots, but probably we need more, we need to work more on science and to involve scientists in this discussion, because otherwise the risk is to have the same approach that is good, of course, of the engineering world, that is more oriented to the application, and is for sure good and great, but we need also to understand really the biological principle, the material, all these aspects, in order to have a robot at the end that are more close to us as a living system, not a really humanoid or humans. And also something that is really more multidisciplinary. So we talk about this, but probably we need to work on this. And this is just, a very simple vision, but because it's a very complex problem. This is the reason. It's not because it's a very complex problem. If in order to address all the issues that we have in mind, we needed to change completely the robotics that we have now, very close to the living system. But in order to do that, we need to change completely the material science that is in robotics now, that is more traditional if you want, the concept to develop a sensing, actuator, the control. So it's a really big issue. So the application is clear, and this is great from my point of view, no? But probably we need to work on the approach, on the methodology. This is just my vision.
Okay, thank you. I don't know if Samia is there, because it is a covered part of my screen. Samia, you are there. Okay. So Samia, what do you think? Biggest bottleneck and biggest opportunity? Samia, are you there?
Hello?
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 Hello? I can hear you. So, biggest opportunity and biggest roadblock
Sorry,
for embodied AI.
Biggest opportunity. I think my presentation this morning explained well opportunities. Yeah, it has been highlighted well through the project that we are delivering. And I think if we could reach the industrialists and really convince them that this technology can reach the industry, then that will ensure the economic growth of the EU. And I think we... can you hear me?
Yes.
I think that we will have to play, I think, a big role in that. Taking all what is happening now in laboratories and try to convince industrialists that this research could be taken further and applied in context of industry, and not only in manufacturing, but in all other sectors.
And you see roadblocks, or you don't see any roadblocks? So you think that we are ready?
No, ready. I think it's I don't think we are ready yet.
It's a provocative question.
No, I know, Fabio, but I don't think we are ready yet. There are quite few. I think I have presented that well in the challenges that we are trying in this project to address. Yeah, namely safety. Safety is critical, as you know. You know, how could we really convince a manufacturer that the system that will be deploying in the shop floor as yeah, then unless we address the problem, then we are not there yet, and that's a bigger problem.
Okay, okay. So, comments or other opinions on these two things from the other sides? We may follow, I don't know if everybody sees the same thing, so the first that I see is Plymouth again, so could you briefly tell what you think, Mark?
Yeah. Well,
briefly, briefly. Sorry.
I agree with the two previous comments, and I had one specific thing that I see as a kind of a practical roadblock right now, and that is to have, if we want to work on embodied artificial intelligence, we depend on interaction with the environment a lot, and so I see a need for robot platforms that are robust enough to be able to interact with the real world without breaking, and that can last over tens of hundreds or thousands of trials without danger to anyone, to danger to itself. So more robust platforms for doing embodied AI.
Okay, good point. So now I see Berlin.
Hello, Fabio?
Sorry? Yes?
Can I just add maybe one point to that?
Yes.
Yeah? Maybe as well, there is something with soft robotics, which is very attractive, yeah, as I said, for manufacturers. But also there is it's still a bigger problem with if it comes to apply that for precise tasks, where the precision is important.
Mm-hmm.
Okay? And I think we've got the control. There is quite a lot to do that, the control side.
Mm. So,
yeah, I agree.
Comments from, I think I can see a blurred image of Verena in Berlin. So what do you think, Verena, if you are there or you are not another person?
Yes, yeah. Well, I also agree with previous speakers, especially with Barbara, that interdisciplinarity is very important. So we really have to cooperate more with fields of biology and psychology, especially. And then another big point is, or the point for the next steps, is to get away from these toy scenarios we're looking at. So we have to really don't restrict us from these toy scenarios, take into account more the real world, and also look at different modularities. So at the moment we're way too much focused on vision, and for example robot audition is a point that has been neglected a lot. And so we really have to look into robots, interact with the real world with many modalities like audition, touch, and so on.
Seems that we are more or less in agreement on most of the talk. So, any comment from Warsaw?
Okay, there is a kind of, how to say, physicists are quite conservative guys, and, to combine this education of this department with robotics courses is not so easy, but I would say this has potential, and hopefully next year we will be able to submit a course for students with ACTS credits. So I would say robotics here mostly is recognized as a multi-body problem with a generalized concept of particle that has internal dynamics. And somehow this robotics, especially agent modeling, can be recognized probably as a part of statistical physics. So that's what I can say from the point of view of people from this department mostly, right? So it's like I try to speak to many physicists. Some of them are a bit skeptical, but still, I think this issue can be promoted in this direction. And also there is neurocomputer science here. So somehow this robotics will be complementary to this specialization. So that's so far what I can say from my perspective. Thank you.
Thank you. Thank you. So maybe we can take a comment from Osaka, since it's getting late there. So maybe you may raise your voice your opinion before it's too late there in Japan. So, any comment from Osaka? What do you think? The biggest opportunity and the biggest unsolved problem? Any opinion? You are too tired to raise an opinion at this point. So we may move to Madrid, where it's still early. So maybe you have an opinion on that. I don't know.
Yeah, the microphone seems not to be working.
Try to use gesture. Okay. Seems that, well, as we noticed several times, this video conference, like AI and robotics and cognition, has been around for decades, but we still have problems, even with video conference. And we want to build intelligent machines, right? So I don't know if we have some other opinion. Otherwise, since it's really, I don't know if there is still if Shanghai is still connected or not. I think we are not there. So since in Asia is getting very late, I really wanted to thanks everybody for attending this another great series of lectures this year, all the speakers, all the attendees, and the students who are still working. So thank you. I take the opportunity also to say happy holidays to everybody, and thank you again. Bye bye.